Brilliant. Okay, let's get going. So, as Sammy said, I'm the Head of Research Data and IP at the University of Southampton. So I will be using a few University of Southampton examples in this talk. And I'm going to go back in time, brief history of academic literature searching, and then talking a bit about the development of open science, FAIR principles and practical tips about your research data. Excuse me a minute. Corrie, please, can you not be in here? Sorry. So the internet's working okay. It's just errant children this time. So taking you back in time to the early 1990s when I was a new professional librarian working at the Open University, and one of my first jobs was to actually teach undergraduate chemists who were on a weekend school how to use chemical abstracts. And back in the 1990s, for almost all of the 1990s, if you're an undergraduate, this is how you looked up chemical literature. And it hadn't really changed much since the 1920s, really. At this point, chemical abstracts came in 9 different volumes. It had consolidated indexes every 5 years, but between those 5 years, you were looking at 6 monthly indexes to find out what had been published in your particular area. If you wanted to look via a particular route, these were the steps that you had to take. If you're an author, it was quite easy. You just looked in the author index, and then you found their name, and then you found all the abstracts that were linked to them. But how many of us actually look for authors when we're looking for, material that we need to answer our research question? We tend to go in by subject or substance or possibly formula. And as you can see, for all of those, you have to start in the index guide, then you have to go to another index, check the authorized term, go to the general subject guide, and so on, and before you find the abstract number. So this is an example of what you would do. If you were looking for vanillin, you'd look it up in the index guide. It would tell you that actually you want sorry, I can't read, my eyesight is getting too bad. You want that particular chemical, so you look that up in the chemical substances. You have to go down until you find 4-hydroxy, 3-methoxy, and double check that you've got the right CAS registry number. And then from there, you can see all the abstracts that relate to that, and you would note down the abstract number. Then you would go to the correct volume for the abstract number, which would mean that you would have to have that abstract number in your head, go along the whole row of abstract volumes till you found the one that would contain that number, dig it out, and this 7-line abstract is what you'd actually get. So to get that far, you'd have looked in 3 different volumes of chemical abstracts. You would have then had to look up your own library catalogue to see if the library holds the particular journal that the paper was published in this case. And in this case, the University of Southampton Library would not. So you would then have to order an interlibrary loan. So you've probably spent for that one article so far a good half hour when you take everything into consideration, and you still haven't got the paper at the end of it. If you're lucky, some of the other abstract numbers that you noted down while looking up those indexes will have been available in your own library, and you'll have actually then been able to go and read them, or at least photocopy them to take them away to read. But it would still be very time consuming. If you were an academic with a budget code, there were other ways. There were online abstracts and indexes available, including for chemical abstracts, because of course they were compiled using databases, but they were expensive. They were command line driven. They were mainly mediated searches by librarians. So you'd sit down, you'd tell the librarian what you wanted. They would translate it into a code. They would do all the Boolean logic. They would type it out and have it ready to go, so they knew exactly what they had to type in, because they were charged down to the 5 seconds that they connected to each service. And then you would get the results in forms of printed abstracts, and you would still then have to check the library catalogue and go and find whether we actually have the holdings. In the 1990s, some disciplines, high energy physics, were ahead of chemistry, still are, I would say, for swapping papers pre-publication. And arXiv did exist back then as an FTP server. But it was a hard slog trying to find out what had been published in your area. And that didn't even get you the underlying data. We're talking all of that work just to get the published journal papers. If you wanted the supplementary information, that was usually published on microfiche, so you could only consult it in the library. If you were lucky, there might be a microfiche printer, so you could actually print some of it out to take it away with you. Otherwise, you would be sitting there handwriting out all of the supplementary information. And of course, that was only for certain journals, not for everything. So it really was a difficult slog. And then the web came about. Now, the first web server was set up by Tim Berners-Lee just at the beginning of the decade. Didn't really go particularly far until 1993, when Mosaic, the first graphical web browser, was released. A few months later, we had the first webcam, which some of you may know was pointing at the coffee pot in computing services at the University of Cambridge. And they'd been pointing a camera at their coffee pot for a few years by that point, but then they decided to stick it on the web so everybody else could see what their coffee situation was. 1993, arXiv also added web access along to its Gopher and FTP access to all of its papers. And things gradually moved on. There was a bit of an explosion. You're all too young to remember, but Al Gore came out and talked about the information superhighway and homes being connected onto the internet, which of course had existed for decades by that point, but suddenly exploded from being a small thing used by defense and academia to something that people used to order pizzas. And in 2000, the very first institutional repository software, ePrints, was developed by the University of Southampton. And that was part of the kickstart to really relook at the whole way that academic research was shared between researchers worldwide. And it was a bit of a disruptive technology for academic publishers. That's a tad of an understatement. So open access at Southampton, as you can see, 2000, we started off with the ePrint software. By 2003, we'd consolidated our various little departmental repositories into one of the first institutional repositories worldwide. And we also brought in an open access mandate. And so on and so forth, as you can see. But open science is more than just open access to journal papers. So the initial push was through repositories to open access to journal papers, either by gold open access, which is paid for usually by the authors rather than subscription forms, which is traditionally what academic publishing was like. But open science was moving beyond that to, wouldn't it be great if we could get everything linked up? You'd always had some early proponents of it, people like Henry Rapsap at Imperial was suggesting that we should have a format to describe chemical information on the web so it would be machine readable, so everybody would be able to search for it using a common standard. And open science brings that in, it's using common software, common ontologies, as well as making the access to the papers and the underlying data open, or at least as open as possible. So this kind of rumbled on as an idea for a couple of years. 2016, there was quite a big leap forward for research data. The OECD published their principles and guidelines for access to research data from public funding, basically saying if it's funded by the public, it should be available for the public. All of the UK research councils definitely agreed with that. They didn't like paying for the same primary research to be done over and over again because the results weren't available. So they brought out research data sharing policies. European funders did the same. Universities such as Southampton instituted research data management policies. And in the early part of the year as well, there was a paper published in Scientific Data, which actually said, it's all very well and good having this data out there, but we need standards for it. And they suggested the FAIR principles for sharing scientific data. Now, just before I get onto the FAIR principles, here is the definition from the University of Southampton of what we mean by research data. It's very difficult to have a single, quick, easy definition for research data. It will mean different things in different disciplines. It's probably easier to say what research data means in STEM disciplines because you can usually bring it down to it's, you know, experimental data or data that we've collected, it's stuff that we're analysing. And that possibly is the best way. Research data is whatever you have used to analyse, to answer your research question. In the arts and humanities, that can be a lot more fluid. It can include, for example, your bibliographies, your list of references, that in STEM subjects you would say, well, that's not actually what I'm analysing. And it may not be, it may just be what you're reading for background as opposed to actually analysing to answer your research question. So, FAIR principles for sharing research data. Stands for findable, accessible, interoperable, and reusable. And under each of these, and I'm just going to page through these quite quickly, there are a number of principles. It's usually that the data should be obvious as to this is the right data. So it should have persistent identifiers. It should be clearly described. It should be registered in an index that's searchable. It should have clear definitions and access criteria. Any protocols used to describe the data set should be free. Ideally, the data set itself should be in a form that can be taken and reused on any different number of systems. And it should be very clear what you can do with the data, so it should have clear licensing. Should use any metadata standards that there are in relevant communities. So how do you go about making your data fair? Well, sometimes it can be a bit daunting thinking about how will I make my data accessible to the whole of the world later down the line. So if you take a step back and think, well, who am I first sharing my data with? Usually it's your future self. It may also be some of your colleagues and their future selves. So take a look at very simple things, just like file names. Would you know what any of these files meant in 3 years' time? Meeting notes from when? Which experiment won? I've done lots of experiments. Which paper did I submit? Which particular revision of my PhD or dissertation is that? And the old canard, as we had earlier, putting final in a file name is never ever a good idea. So get the metadata into the way you work. Think about your folder structure, think about tagging, think about document registers, think about name, formulas. You know, how are you going to have a strategy to keep on top of all of your data? So, folder structures. You could have one big fat folder versus hierarchical. If you're going for hierarchical, don't make it too deep because you'll get frustrated at clicking down and clicking down and clicking down. On the other hand, having one big fat folder may be okay for certain projects, but in other cases, it might actually just be too confusing and you're going to try and put too much information in file names to be able to distinguish them if you've just got everything in one massive folder. If you're using systems that allows you to tag metadata within your files, so for example, all Windows software will allow you to add titles, to add subject information, to say who the author is, then do that. If need be, you may need to keep a record of what files are where in a spreadsheet, which I'll get onto and show you an example of that in a minute. This is another cartoon like the final one that Sammy showed you earlier from PhD Comics, which is a huge time sink, but can sometimes be good for the soul because it reminds you that everybody has been in your position. This is definitely a do not do as I say cartoon for renaming. So choose sensible file names that will mean something both to you, to your future self, and to anyone else who needs to look at your data. And keep a record of any abbreviations you've used. Abbreviations are great, but if you don't keep a record of them, you might forget. You may think you'll never forget, but believe you me, you will forget. And if you're doing a project where you may need to share your data beyond yourself, you need to have that list of abbreviations because you will need to provide a README file for whoever else is looking at the data. So this is an example from social sciences, FG1. FG stands for focus group, cons is for consumers, and the date is in year, month, day format. Once you know what the abbreviations stand for, it's very simple to understand what is going to be in that file. Now, I said you might need to keep on top of your files using a spreadsheet. Now, this again is an example, not from STEM subjects, but I've known chemistry PhDs who've used this sort of way of keeping on top of their files and keeping on top of the metadata that's associated with the results in each file, because they found that the process they were using meant that some of the metadata was lost as files and samples went through the process. So you can have document register, running number for the various documents. You can list the title, bit of a description, date it was created. the all-important where it's actually kept. And then you can add any number of tags. So it might be that you're talking for experimental data, you might want to have the batch numbers of the chemicals that you were using in particular experiments. I know a social scientist who uses it to actually tag what is being shown in the image. So she has lots of different subject keywords, and she selects all the ones that are relevant to the images that she's listing in her index, and so on. Again, another way of naming your files. This one has a prefix for the type of document, and then a title, and then the version number, and then the date. And again, the date is always in the 4-digit year, 2-digit month, 2-digit day. If you are putting in version numbers into file names, do remember minor revisions. If you're using standard convention, use point changes. Substantive changes, you'll then have a completely different number. So you'll change the main number, not just the point. And the reason we say use the 4-digit year, 2-digit month, 2-digit day, well, here's an example of folders and files that were pulled off different areas of the University of Southampton SharePoint system. The one on the left is from a meeting that happens every week. Not that you'd be able to tell that by scanning your eye down the dates, because the dates are all over the place, because they're in the natural order that we would say the date, but that's not natural for an index on a computer. Files on the right, unsurprisingly, they're from a library meeting, so they are thankfully correctly named, and they will just index naturally in chronological order. And as you can see, we've put a suffix after the date on some of the files because it's supplementary material to the meeting from that date. If you are working on a document with several people, Sammy has already gone through some really useful things that you can do. You can also, depending on what you might be doing, put a version control table at the top of the document so you can keep on top of who's done what, who's checked things, and who altered the file last. It does rely on your collaborators actually filling in the version control table, but this is something that you will see, I'm sure, in your time in documents, particularly well used in industry, in particular for version documents of policies and procedures, so you can see when it was last updated and what all the previous updates were as well. And there is version control software that you can use if you want. Two of the main ones are Apache. Apache is open source, so you can download that and use that yourself. Mercurial is also free. Many institutions run a Mercurial server. We do here at Southampton. And Git, again, Sammy's mentioned this. You can either use the main GitHub, or again, many institutions will run their own Git version if you want your files to be private, although I think the main Git now allows you to set privacy levels on your files as well. So storing your data, you need to think about what you need to store in the short term, what might need longer significant term. So what are kind of working disposable files? What are the things that need to be kept longer? Think about, you know, I might be using this in this marvelous whizzy piece of software now, but not everybody will necessarily have that whizzy piece of software. Is it possible to get the results out of that into a more archival format later down the line? something you've probably not needed to think about before, but it is useful to just have that in the back of your head about, you know, if I needed to look at this data again and I didn't have access to that software anymore, you know, could I? So for those of you who aren't at Southampton, you may not have seen these photographs before. This is from the fire that led to the largest insurance claim in UK higher education history. It's when our clean rooms and the attached building and offices went up back in 2005, the day before I started working at the university. This is why you should always back up and not just have your material in one place. It could happen to anyone and it could not be your fault at all. But if you've backed up, you'll be okay. So standard rule that's quoted all the time is 3-2-1 backup. So have 3 copies of the data, preferably on 2 types of media and 1 copy off-site. If you use whatever storage system that your institution offers, you can almost guarantee that they will have that sorted for you. If you choose not to use the institutional storage, then you will have to make sure that you've got 3 copies of the data on 2 types of media, and 1 of them off-site. By that, I mean, don't keep them physically in the same place. Because we did, on those horrible offices, we did have some PhD students who had all of their material on their hard drive, were backing up to CDs because this was nearly 15 years ago. And when the office went up, they lost everything. Those PhD students who'd been backing up onto their server were fine because the server had tapes that were off-sited regularly. They may have lost a couple of days' work, but they didn't lose months, or in some cases, we had some students who lost years of work. And as Sammy will tell you, if you don't back up and you lose years of work, even if it's just your references, it can feel devastating. So, back up regularly, preferably using institutional resources because they will be doing all of the hard work for you. Something like OneDrive for Business, which you can also access using SharePoint and Teams. They all use the same technology underneath them. It's cloud-based, the data's encrypted at rest. If you're in the UK, the data's held in the UK. If you're in the EEA, the data is held within the EEA, so it is compliant with all GDPR requirements. Unlike if you use personal OneDrive or you use Google Drive. So for work that you are doing as part of your institution or work for another institution, please use the institutional resources if you are able to, and you should be able to. Things like SharePoint, even if you're not at Southampton, but you're working with people who are at Southampton, they can set up a SharePoint and give you access to all of the files on that SharePoint, and you can work on the files on the remote SharePoint, and then all the backing up, the encryption and everything will be done for you. The file naming and the version control, again, still something you need to work on yourself. I remember things like data sticks are not storage solutions. You know, sticking material on a data stick and putting that somewhere is not what we would call a proper archival storage solution. So, FAIR. You've got your data, you've been doing your data, you've been doing your research, you've been naming it well. It needs to be findable and accessible at the end. If you need to share your data, outside your research group, the best place to put it is a repository, and the best place to put it is with like material. So if you're doing, for example, genomic research, you put it in a genomic repository. You don't put it in your local university repository. There's no need, no point. People won't find it. It won't be able to be described in its fullest way because your local institutional repository will not have the depth and richness of metadata in their records that a genomic repository would for genomic data. Likewise, there's no point putting ecological data in a genomic database. It won't have the right metadata fields to be able to describe the data richly. So try and put it with like material in a subject or disciplinary specific repository. That's not always possible. They don't all exist yet. Even now, 5 years after the FAIR principles were released, we still don't have, in the UK, a nationwide network of disciplinary repositories, and we are still very much relying on institutions to pick up the slack. Any repository where you do deposit data should give you a DOI. So if you're putting it in a generic repository like Zenodo, they will give you a DOI for the data set. Institutional repositories, for example, like ePrints at Southampton, we will give you a DOI for the data if you ask. Many universities within the UK will also require you to put a record in their institutional repository, even if you've got your data held elsewhere. That is because of funding requirements from the UK research councils. So if you do put your data elsewhere, tell your university repository where it is. Otherwise, your institution will not necessarily know where all the data that was created in the institution is being held. And you should make a README file for any data that you are depositing elsewhere. And that README file should quote the DOI for the data set, because otherwise they may get separated at some point. And it should also list any associated papers, and likewise in the associated papers, so if you've done any publication, whether it be a conference paper or actually a journal article, have a data statement in there saying where the underlying data can be found. For a DOI to be issued for your data, the actual requirements are really quite low on the metadata. They just need to know the title, the authors, and a short description. So that's not going to be as full as it could be. It's not going to have as much information as you might be able to give it. So for example, you don't have to put in any SIF data if it's crystallography. You don't have to use SIF data to be able to get a DOI, but for people to find your material, you'll want to have disciplinary metadata in there as well. And these are just examples of some forms of data statements that you will begin, hopefully, to notice in research papers as you read them, that these should be becoming more and more standard. And for those of you who've authored it, you should be using an ORCID ID. If you haven't got one already, get one. It's a persistent identifier for you as a person that stays with you throughout your career. It doesn't matter which institutions you move to, doesn't matter if you change your name. You know, it's also funder independent. So this is a data set that's one of our most popular data sets at the University of Southampton in our repository. And it's in our repository because there isn't really a repository that was better for it to go into. But it has thousands of downloads per year. So people are finding it, even though, as you can see, it is quite limited in its metadata because it's in a generic repository as opposed to being in a subject-specific repository. And again, meeting the FAIR principles, data doesn't necessarily need to be openly available. It can be on request. It can be restricted to certain users. You know, you may have to show that you've got ethics clearance from your own institution to be able to access the data. Not being immediately openly available does not mean that your data set is not fair. What makes it fair is that it's very obvious and clear to the requester how they get access to the database, data set. Interoperable data. Can you still read your data in 20 years? You can usually still read text files. If you can save your data into a text file, brilliant. It might be comma-separated variables, marvelous. But you can use other markup languages, particularly if they're disciplinary specific, as long as they are openly available formats. And for other types of non-textual data, there are standard recommendations for digital archiving. You can find those at the UK Data Service in the UK. Other versions of that table are available from the Library of Congress and other national libraries as well, but it is a general international standard that's used for digital archiving. And if you can save your data into one of those formats, that's better than just leaving it in a proprietary format. Obviously, some formats are very, very long-standing. This is Galileo's notebook from ink on vellum from the 1620s. And you can see his observations on the left-hand side, the metadata showing when the observations were made. And then you've got further descriptive information, his kind of README file at the bottom of the right-hand page where he's actually working out the orbits of the Galilean moons around Jupiter. And if you can read medieval Latin, which I can just about, that information is still understandable 400 years later. As I mentioned, there's also markup and additional information that you can put on your data sets. Again, this is still very much an emerging field. I would have thought in another 20 years' time, we will have far more disciplinary metadata than we do at the moment. It's taking its time, but it will get there. And letting people know that your data is reusable. Obviously, have your README file, make it well cited, give the provenance of where this data has come from. So not just saying this is how you can understand the data, but what's the research group? Which institution is it? When was it collected? Where was it collected? May not be useful for some of your data, but for example, ecological data, very, very important. Any licenses on the data, any publications linked to the data, what was your methodology? What instrumentation did you use? What were the settings for that instrumentation? How did files relate to one another within the data set? A little bit of information about what's in each file, any abbreviations used, what the column headings mean in tabular data, and so on. And licenses, you should be thinking of things like Creative Commons licenses that can go from very restrictive to almost free, or if you want to put it into the public domain, CC0, but then you won't get cited if you put CC0. So while for some cases CC0 is great, for other cases you actually want people to say, well, that data came from this research project, so you do want that citation there as well. So, any questions? I think